Hi, we are Group E, and this is our presentation on Euler circuits and Euler paths. A connected graph has a Euler path if and only if it has two vertices of an odd degree, and all the other vertices are of an even degree. Every path must start at one of those odd vertices and end at the other. A Euler path must also use every edge exactly once. So, if an edge is used more than once, or there are more or less than two vertices of an odd degree within a graph, then there is no path.
A Euler circuit is a walk that uses every edge exactly once, starts and ends at the same vertex. Its close cousin, the Euler path, which traverses each edge of that graph exactly once, without going back to any of the already used edges. Often mixed, but they are both collided and often found together in graphs. If a graph has any odd vertex, then there are no Euler circuits. Also, to count as a Euler circuit, it must be a connected graph. Some real-life examples are often mail delivery and street sweepers, all because of the distinguished route they must follow, and each stop being stopped at once, and ending at the very beginning, such as a Euler circuit would.
There are several key similarities between Euler paths and Euler circuits. The similarities between them are that they are both a part of graph theory. They were both created by Leonhard Euler, and an Euler path and an Euler circuit both can only use each edge exactly once. In addition to there being several key similarities between Euler paths and Euler circuits, there are also several key differences. The differences between them are an Euler path doesn't require one to start and stop at the same vertex, whereas an Euler circuit does. Every Euler circuit has an Euler path, but not every path has an Euler circuit. And the vertices of an Euler circuit must all be even, while the vertices of an Euler path must have two vertices of odd degree, meaning that if there is a graph with only one vertex of odd degree, or more than two vertices of odd degree, it cannot be an Euler path.
This graph is an example of a Euler path that uses cities and roads. To check if a Euler path exists, we can count how many cities have an odd number of roads connecting to them. In this graph, two cities have 3 roads connecting them, while all other cities have an even number of roads. Since exactly two vertices have an odd degree, a Euler path is possible. One possible Euler path goes from Burley to Dover.
Königsberg Bridges problem. Euler used it to explain an Euler circuit, which in this case is a path that crosses each bridge exactly once, and then returns to the starting point. In the example behind me, each area has an odd number of bridges, so it's impossible to do this. To have an Euler circuit, each land area must have an even number of bridges, as each vertex must have an even number of edges.